now that we have taken a look at electron configurations, seeing how things are stacked up, I talked about valence electrons. Now we're now going to see how those interact with one another to form the different kind of compounds that we've been talking about. We know how to name them. You can tell me how many things are in it, like how many oxygens are there, how many nitrogens are in a compound, that kind of thing. But to truly understand how something behaves and to truly understand how it's going to interact with nature, you've got to be able to think of it in 3 dimensions. You've got to be able to imagine the whole shape of it and how it's going to be tumbling, through space at any given time. Because what you'll find out is the number of valence electrons that we're dealing with determines how, like this hydrogen, for example, will stick onto this carbon. And why there are 4 hydrogens around one carbon. What can cause a carbon to stick to another carbon? If this chemical right here, which would be methane, will be one carbon with 4 hydrogens around it. Why does it behave the way that it does? We understand now why these stick together because of the valence electron stuff we've talked about, trying to be happy. They will share electrons so that everybody can be happy and reach the state that they want to be. But why does the methane molecule as a whole, then, as it's floating through space, behave like it does? Why does the whole thing react with other stuff? Why can you put energy into it, light it, and mix in oxygen and get a combustion reaction? And you've got to think about many more things than just the stuff that we've been talking about. Now we've got to step up to a bigger picture and look at the whole entire shape and dimensions of a molecule. And we have to understand what we've just learned in order to do that. So that's what this is about. Okay, we're talking about the way that atoms attach to make molecules. As long as we can learn a little bit more about that, we can understand why they do this. If we look at how they do this, we can then understand why they do this, and then we start being able to even further explain the things that we see in the lab, things that we see in nature. Okay, we can predict shapes. Once we know shapes, we know properties. We can start guessing because of what's there. Like, for example, if this was an oxygen, if these 2 hydrogens were gone, and instead what you had was this stuck together, you had an oxygen. The red is oxygen, the black would be carbon, and the 2 whites would be hydrogen. The properties of this molecule is entirely and totally different than that one I just showed you. Okay, so the shape that we're dealing with here is very, very important. And we have to, consider a lot of things. Think in 3 dimensions in order to do this, and that's what we're going to hopefully be able to do when we're done here. Perhaps more importantly for you as allied health people is you think of the pharmaceutical industry, and this is how it works. You can build new things. If you know how molecules are organized, and you see, like here, there's a definite oxygen end, and there's a hydrogen end over here, this end is actually going to behave differently than this end over here. And what that allows you to do, the more you understand that at a deeper level, it allows you to take other things and hook on with it and build bigger things. You can actually build specific things that will have specific properties. If you say, okay, I want a molecule that's able to do this, or I want a molecule that's able to do this, well, you can take what you know about all this kind of stuff, start hooking stuff together, and know and be able to know by looking at the structure of it how it's going to behave. That's how we can make things like polymers, plastics, Teflon, pharmaceuticals, things like that. There's a whole industry about synthetic chemistry and how we build things. Okay, so in order to sort of simplify this and get to a point where we can make some sense out of it, one of the things you're going to have to learn is what's called Lewis structures, or dot structures, or electron dot formulas. They have many names. All you really need to know to write one of these is the number of valence electrons that something has. Now, most of the time, you can just look at the periodic table, and you can look and see what column it's in and predict how many valence electrons it will have. But you can always write out the electron configuration and find it. You have enough power in your hands now to figure out how many electrons, valence electrons, something has. Once you know that, to write a dot structure for something, all you need is the symbol, and you see a bunch of dots around the outside of these. And if you count them up, lithium has 1, beryllium has 2, boron has 3, carbon 4. Those dots represent valence electrons. How many valence electrons does this particular atom have? Okay, so the way that you would do this, if you're actually writing it all out, lithium has 1. Think of these like a box around these elements. And what you'll want to do is, if you have 2, instead of putting, just like in orbitals, instead of putting 2 electrons in orbitals, the same one, you'd space them all out first. Do the same thing here, but one on one. The reason this is bigger is don't worry about that. It's just formatting. Okay, you don't need to draw one bigger than the other. Put one on one side, one on the other side. Doesn't matter which side you pick. I don't care. That's beryllium. Lithium, just pick a side, put a dot on it. When you get down here to boron, same thing. When you get to carbon, it's got 4, so fill up all 4 sides of that box first before you move on. And then when you get to nitrogen, just pick one. Doesn't matter where you start. Then you start doubling up. So that you'll see, since we deal with 4 sides, the most that we're ever going to be able to have then is going to be 8. Right? So if when you look at neon over here, 2, 4, 6, 8, it has 8 valence electrons. Okay? Now this becomes important because it allows us to keep track of things. And for every valence electron that something has, it's an electron that can either be given or taken or shared with something else. So it allows us to keep track of valence electrons and what's happening. Okay. All right. So that means what this is saying is that we said elements in the same group, sodium, lithium, sodium, potassium, all those guys in the same group, all have the same number of valence electrons, right? So they should all have the exact same Lewis structure. Sodium should have 1 dot like lithium, and as would potassium. Okay, so you're going to have a lot of things in the same group with the same Lewis dot structure, okay, Lewis symbol. All right, now remember what we said, that atoms are in a state of seeking towards a noble gas configuration. Now, the only way they're going to be able to do that is to mess with their electrons. They're either going to have to give up electrons to get there, like sodium would. They're going to have to gain electrons, or an electron, to get there, like chlorine would. Or it could be that you got 2 things that have such a high level of ionization energy where when they are pulling, like say you have 2 nonmetals close to each other, like sulfur and oxygen. They're both on the right side of the table. They both want to gain electrons to be like their noble gas. When you put them together, you do get a reaction. But realize that no one's going to want to give up their electrons when you have sulfur and oxygen together. They're both going to want to try to take electrons. Well, it just so happens that one doesn't get to bully the other. One's that much stronger than the other. So what happens is they are forced to share electrons instead of one giving one up and one taking one. And that results, I'll show you how, but that results in both of them then being able to have what they want, even if they don't want to share. You have to. And they can do this and achieve a stable electron configuration. So that's the reason that bonding exists. That's why chemistry exists. Because these atoms out there are constantly trying to be like the noble gases that are out there. So they will always hook up with something else that will help them to that end. They will always try to reach that stability by bonding with other things and messing with electrons. I talked about the octet rule already. Things are looking for, the configuration of noble gases have 8 electrons on the outside, except for helium, right? So, in general, things are happy with 8 electrons in their valence shell, and they will try to move towards that end. They will try to gain electrons to get 8 in their outermost shell, or they will try to lose electrons to drop down to the shell below them to allow them with 8. Okay? Like I said, there's a few exceptions. Helium only wants 2. That means hydrogen only wants 2, and lithium. But exceptions we'll work with as we go along. The key is just always remembering that they want to be like a noble gas. Okay, now you can write Lewis symbols of ions just like we could write electron configurations of ions in the last chapter. So what would happen then, think about it. Cation is your metals that form positive charges, right? Look down here at lithium. If it loses that valence electron, the way that you would write it, okay, in terms of a Lewis structure, is what you see here. Just write it like you normally would write the ion. You write lithium with a 1 positive charge. And what that means is that you had lithium that looked like this. Now that dot's gone. It lost it. So that's what you're left with. Okay. What we do is want to just keep track now of changes that occurred. That's what this is for. Anions, the negative ions then, are going to move from, like in the case of fluorine, it had 7 to start with. If it gains one more, draw that one in that it gains, and then realize that because you've added that one electron now, it's not like it was in the charge-neutral state. It actually has a charge now, and I want you to indicate that to me. So you would have fluorine with 8 electrons, brackets around it, to offset it with a -1 out to the side. Okay, so electron dot structure for a positive ion, a cation, is just write the ion, because the whole point is to show me that this lost its electron. It's gone. Over here, 7 electrons around this fluorine atom. It's going to gain 1 to form an ion, a -1. So put that other dot in there to show me that you know where it went. Draw brackets around it, give me the negative sign. Okay. Now, remember we talked about ionic compounds, right? Back when we were naming things. And the one way to recognize an ionic compound is when you have what two things stuck together? What two things stuck together make an ionic compound? Two sides of the table, right? So a watt and a watt. A metal and a nonmetal. Okay? A metal and a nonmetal is going to result in an ionic compound. And so the same thing is when you deal with an ionic bond, is when two things come together, and they're generally going to be a metal and a nonmetal, because what's going to happen is a metal will give something up, and a nonmetal will take that electron. Okay, so this is going to result in an ionic bond. The metal actually loses electrons to form the cation. The anion, or that will form, the nonmetal, will actually gain that electron. That's how it got its negative charge. So the bond that you get results from now the fact that you have something positive and something negative, and that force is what's holding this thing together, okay, because of that movement of electrons. Now, the larger the charge, the stronger the attraction. So what I mean is, if something that loses that one electron versus something now that loses 2 electrons, and the actual value of the charge gets bigger and bigger, the more the attraction is that's going to hold this thing together. That's what this is saying. Okay. All right. So when we know about Lewis theory, that allows us then to predict the formulas of ionic compounds. Now, you've already done this just in a way that you've memorized, but now you start to see why. Why, for example, calcium chloride has to be what? What's the formula for calcium chloride? CaCl2. Ca is a 2 positive. Each Cl is a 1 negative, right? So if you're going to put 2 of them together, you've got to have CaCl2. Now we start to see why in terms of electrons. Oh, I just happened to pick the right one. I didn't even know that was next. If you consider calcium and chlorine, let's draw the dot structures for each of those and see how each one of them are going to interact with one another. Calcium has 2 valence electrons, right? Chlorine has 7 valence electrons. So I've got these 2 atoms next to each other. All right. Excuse me. What will happen here is chlorine wants 8 electrons to be like the noble gas in front of it. Calcium wants to lose those 2 to fall back. So what will happen is if you put chlorine in with calcium, chlorine will take this chlorine right here will take one of calcium's electrons, right? So move that over here. There you go. That leaves calcium with 1 extra electron. It is not happy. It's not going to work this way. If I stopped it right here, that's why, for example, calcium chloride cannot be CaCl. Because if you just wrote CaCl, that means 1 calcium and 1 chlorine, right? If that were true, and you tried to do that, you would end up with a chloride ion now that's happy, but you would have a calcium that's still got 1 valence electron. It's not going to work. It's going to seek out somewhere else to get rid of that valence electron. That's why it can't be CaCl. However, if you have Cl's floating around, another one will come up. It wants an electron as bad as he wants to get rid of that electron. That electron will leave and go to the other Cl. So it took 2 Cl's, because each one of them only wanted 1 electron. It took 2 of them to completely satisfy calcium here. Okay, does that make sense? You see what I'm saying? So as a result, you needed 2 Cl's to take away those 2 valence electrons that calcium had. That's why it's CaCl2. Now, in this case, the way that you would write this, you can actually write a Lewis structure for this entire compound, for the CaCl2 compound. Instead of just writing the formula, you can look at it in terms of where the electrons went. Okay? And the way that you would do that is just write Ca. What you'll also find is as we go through this chapter, as we put more and more atoms on each other, nature has a way of working in a very symmetrical pattern. So if you have two of one thing and one of another, chances are that one thing is going to be in the center and the two things are going to be on both sides of it. It all sort of balances out. So in this case, we would put the calcium in the center. It lost 2 electrons, so it's got a 2 positive charge, right? And on both sides, I've got chlorine that went from 7 to 8. I reflect that in here. My brackets, 1 negative after it. The formula would be CaCl2. This would be the dot structure for it. You follow me? All right. Then we have what's called covalent bonds. So in ionic bonds, the key was an electron actually moved. It physically moved from one atom to another. Okay? What you'll find is that sometimes bonds exist that don't involve a metal and a nonmetal, and you don't get movement of electrons. What you end up with is what's called a covalent bond. And covalent bonds result in sharing. They have to share these electrons. I don't know why I just had Tourette's or something with my knee. So what you get here is a very, very strong attraction, sort of like the difference between just standing next to somebody versus like interlocking your arms and holding hands and locking your legs and everything else. When you have overlapping, you'll find that the electrons overlap in some of these guys. It's a lot harder to pull them apart. These ionic compounds realize that the only reason that they're next to each other is because one now is positive, one now is negative, and they sort of are attracted to each other because of that. With the case of covalent compounds that result from sharing of electrons, they're much more tightly held together, and it's hard to get them to separate from one another. Okay? All right. And what will also end up happening is, if you think to, remember that lab we did with when we dissolved all that stuff, or sorry, we did the precipitate lab, and we talked about net ionic equations. I talked about how water worked and pulled apart all the ions and all that. Realize that an ionic compound is made of something that's positive and negatively charged, right? And that's holding it together in solid form. If I put that in water, it falls apart very easily because there's negative areas of water and there's positive areas on a water molecule, and they can pull that ionic compound apart. If I put something like oil in with that water, you know that it doesn't mix, right? There is no area, there's no positive negative area on some of these chemicals that have covalent bonding, because everything is shared and overlapped. There is no positive negative. There's nothing that took and nothing that accepted. So as a result, the molecules themselves are generally weakly attracted to each other. For example, CO2. CO2 results from sharing of electrons. All the forces that's holding it together is sort of, not exposed to the outside, and it's inside and holding the CO2 together. So if I put another CO2 next to it, they're not attracted to each other very much. Whereas if you have something else that has like positive, negative sticking, it's held together by positive and negative forces. You put something else that's got positive and negative forces in there too, you can mix that up and you can see where they could intermingle with each other very easily. These guys here that are shared together, they don't get that positive, negative result. So they don't mix together very well at all. Okay, take a look at, we'll first look at single covalent bonds to give you an idea what I'm talking about here. Two atoms are going to share one pair of electrons. Now I'm talking about a pair, that means two. Okay, so take a look at fluorine. Fluorine has 7 valence electrons around each atom. If I don't give fluorine anything else to react with, and I just give it other fluorine atoms, and I put them in a vessel and it's fluorine gas, and I let them intermingle with each other, they will react. Okay, but they won't react like they would with sodium. If sodium was present, what would happen is sodium would give up its 1 electron to make itself happy. Fluorine would become fluoride because it would take that 1 electron. You would have an ionic compound, sodium fluoride, right? You would have a positive-negative situation. However, in this case, you're not going to have one because you've got 2 fluorines And both of this guy really, really wants one more electron, but guess what? So does this one. And it becomes a game of tug of war, almost. It's like, if somehow this guy could pull hard enough, this guy loses. He ends up giving his electron whether he wants to or not, and this one could take it. But that's not what happens because it's a very fair and balanced fight. What will happen here is they both want this electron, so they settle. They say, fine, let's do this. Let's bump up next to each other. Let's take this one that we both want, and let's just share it. Okay, let's be happy. And what happens here is the orbitals that this electron is going to move around in, they overlap. Okay? So what that means is it doesn't really go to any body, but it goes to a point where it can be equally accessed by either atom at any given time. So that means it's satisfied because it has, even though it doesn't in its personal possession necessarily own 8 electrons, it at least has access to 8 electrons at any given time if it wants them. So 2, 4, 6, 8. At any given time, these 8 can be associated with this fluorine. 2, 4, 6, 8. At any given time, these 8 can be with this fluorine. Right? Now, since there's 2 electrons being shared, the way that we abbreviate it in this chapter is just draw a line between these things. So anytime you see a line, what you got to realize is that means there are 2 electrons for every line that you see being shared between these atoms. Okay? So that would count. Like if I was counting up all the electrons I saw here, it would be 2, 4, 6, 8, 10, 12, 14. Right? All right, now let me ask you a question. I mentioned that on the periodic table, there were such things as diatomic molecules. Remember those? NOF, Cl, Bri? Now we see why those exist. Take a look at chlorine. I don't know how that jumped way over there. The pen's not working. Take a look at chlorine. It would have 7 valence electrons, just like fluorine would have, right? So if I put 2 chlorines in a sample and they couldn't react with anything else and only had to react with each other, guess what they would do? The same thing that fluorine just did. They would have to come up to each other in pairs. Covalently, they would share that electron. They would form a covalent bond. And then it would be F2, Cl2, O2. They would do the same thing. And this is why some of these diatomic gases exist. This is why they do that. Okay? All right. Now, take a look at H2O. We got water molecule here. If you look and try to figure out why water is stuck together, you realize that it's not going to be ionic in nature. It's not a metal and non-metal. We've got 2 non-metals here. You look at oxygen. Oxygen, if you do the configuration, you'll see that it has 6 valence electrons. Each hydrogen has 1. Oxygen wants to be like the noble gas. It wants to have 8. Hydrogen wants to be like the noble gas closest to it, which is helium. It's going to have 2. How can this pattern come together to make everybody happy? And there's only one way that can happen. What can happen is they can straddle that oxygen, and that electron and that electron can be shared by both of these guys. That electron and that electron can be shared by both. And what you get is, when you look at this overlap, anything that overlaps, any bonding electrons we write as a line, you get this. Now, is everybody happy? Each hydrogen has access to 2 electrons. The oxygen has access to 8 electrons. It's a covalent bond. It's sharing. It's much harder to bust up this bond. It's much harder to break this bond than it is to take like sodium chloride, for example, and break it apart. Take sodium chloride, drop it in water, it dissolves. It falls apart very easily. These covalently bonded molecules are much harder to separate out and bust them up. Now, however, it gets trickier. What about oxygen? I told you oxygen was also an example of a diatomic molecule, but it's got a little bit different structure than the halogens have. Take a look. Oxygen, in a pure sample, has nothing else to react with. It will react with itself. It's not going to be like Na2O. It's not going to be like sodium oxide, an ionic compound. You're going to end up with a covalent compound, a covalent molecule. It's not a compound. There's not 2 or more elements present. You got 6 electrons here, 6 electrons here. Put them together. How can you possibly figure out a way for both electrons to be happy? Well, there's only one way to do that. I'll show you sort of how to systematically figure this out. But there's only one way to do that. If I take these, let's say these 2 and these 2, and put them in a pool in the middle and allow them to be shared, this oxygen then will have access to 8. This oxygen will have access to 8. But notice what had to happen. They had to not just share the one pair. They had to end up sharing 2 pairs of electrons. That's why there's 2 lines between the oxygen. What do you think is harder to break apart? A single bond or a double bond like this? Definitely a double bond. Okay? So an oxygen is even harder to bust up than would be a chlorine or a fluorine or a bromine, any of the halogens. Oh yeah, they can. Yeah. It's not so much, the question was they can rearrange their electrons. It's not so much they can rearrange them, but because we never really know. Remember what we learned about electrons? We don't know where they are at any given time. This is all probability of where they're going to be located. I don't know about rearranging in terms of moving things around, but definitely what they have the ability to do is some of the electrons that they have the ability to be here at that point, to be able to be shared. So, all right, take a look at this one, nitrogen. Nitrogen was the other, besides we had the halogens, and then we had oxygen, nitrogen, and hydrogen. Those were our diatomics. So let's continue to look along those lines. Take a look at nitrogen. Each nitrogen has 5. If you have a pure sample of nitrogen, you've got all these atoms that have 5 electrons around the outside of them. How can they come together, 2 of them come together in a way so as to balance it out and make it have 8 like it wants? Well, in this case, it would take these 3. That will take these 3, put them in a pool. They'll share them. Okay? And if that's shared, you'll notice that 2, 4, 6, that was behind this down here, 8. There's 8 electrons here at any given time. There's 8 electrons that are accessible here at any given time. They're happy. Notice what it took, though. It took 3 bonds. It took 3 shared pair of electrons to make that happen. That's a triple bond. Stronger even than a double bond. Very strong. What you'll also find is the distance between, the stronger that bond, the closer the atoms are together to one another. So when you have like chlorine, for example, chlorine gas, Cl2, say they're this far apart. You have oxygen. The 2 oxygens are only about that far apart. You have nitrogens. They're only about that far apart. They're much, much closer as a result. It's a stronger bond, and the atoms get closer together. Okay. All right, so that would be a triple bond. You can have double bonds, single bonds, triple bonds. All right. So anything that's shared in that pool that's part of making that bond we call bonding pairs, okay, bonding electrons. And then whatever's left, just decorated around the outside, not really decoration, of course, but what's on the outside, like these 2 and these 2 that are not involved with the bonding, those are called lone pairs of electrons, or non-bonding pairs. So now, interesting thing about polyatomic ions, why they behave the way they do, why I had you memorize all those polyatomic ions. Polyatomic ions, at the time, I just had you memorize them because otherwise we couldn't have got where we are because we had to use them in the stuff to learn up until this point. See, chemistry, that's the thing. There's no really good starting point because now we can understand why polyatomic ions are the way they are. You can understand sort of the reason behind their formulas and the charges that they have. But we couldn't have learned about chemical equations and all that kind of stuff without having just memorized the polyatomic ions. Now we can go back and sort of understand the why. The polyatomic ions are attracted to one another. Like if I have ammonium, which is NH4 positive, right, and I have sulfate, which is SO4 2 negative, SO4 2 negative, I can put those 2 together, and they are attracted because of their opposite charges. But realize that inside those ions, to make them, like SO4, guess what? I've got an S with oxygens around them. I've got covalent bonding that's holding those nonmetals together. So I've got covalent bonds, and then the big picture, after I've got the covalent bonds that are holding that thing together, it acts as an ion that participates in ionic bonds. So it gets a little confusing, but that's what this is saying up here. The atoms inside the polyatomic ion are held together by covalent bonds, but the polyatomic itself participates in ionic bonding, so it acts as one big ion. All right, so that's why we need to know these Lewis formulas so we can see when we're trying to draw pictures of molecules where they're going to orient themselves, how many electrons they have to give, how many of them are going to be there, that kind of thing. And it gives us shape. So, some things that you're going to see, you don't have to memorize this yet, but the more you work through this, the more these will become apparent to you. There's going to be some common recurring patterns that you're going to see. For example, one thing that you're going to notice, this one's an easy one, is carbon. Carbon has 4 valence electrons. So that means when it shares, the most amount of bonds it can have coming from itself is 4, right? Because if something else got an electron and it's got an electron, they can come together and form a shared pair, right? So it can form 4 different pairs of electrons. So carbon actually has 4 bonding sites. That's what I showed you to begin with over here with the white. If this is methane, it's got carbon and 4 hydrogens on the outside. If carbon has 4 bonding sites, it has a place for 4 covalent bonds. Boron will usually only have 3. It'll have actually only 6. I'm not going to get into it, but it actually only has 6 to make it happy on the outside because of where it's at. Nitrogen will almost always have this structure right here that you see. It will almost always have 1 lone pair and 3 bonds coming off of it like a tripod off the bottom. Oxygen will almost always have 2 bonds instead of forming more. You'll see why in a little bit later. But oxygen will almost always have just 2 lone pairs and 2 bonding pairs. And things like halogens in general, okay, all halogens will generally only be terminal. The only place they're usually going to fit is on the very end of a bond coming out. Like, you can't have a halogen in the middle of something. If you think about it for a second, you'll see why. It only wants 1 electron, right? It only wants to form 1 shared pair. It's not going to form more than that. If you try to hook something else up and form a shared pair, you end up with 9 electrons for fluorine. It doesn't want 9. It wants 8. Okay? So you'll find that a lot of those things, like hydrogen that only wants 2, fluorine that only wants 8. Fluorine is going to usually be terminal as a result of that because it can only form 1 bond. You can't fit in the middle of anything because nothing else can stick off of it. And the same thing with hydrogen. It only wants 2, even though that one's not up here. But I'm just so I can refer back and point these out as we run into them. You'll start seeing why this is the case. All right, now there's a lot of instructions here I'm not going to read over. I'll let you do that as you're practicing. What I'm going to do is go through an example that will incorporate all these steps. How to draw a Lewis structure. For example, let's say I want you to draw the Lewis structure for HNO3. What I mean is I don't want just the formula now. What I want you to be able to do is to show me how these atoms are going to be positioned relative to one another. What's going to be where? Not only that, where are any electrons going to be located? Okay, how are they going to be distributed? Because once we start learning that, we start understanding why things behave the way they do, and what you could stick with that to get a reaction to occur. Okay? So take a look at this. One thing to keep in mind, I picked a couple here that are HNO3, then I do a nitrate group here in a minute. Those are the most difficult ones. The rest of them are easier. So if you can do these couple examples, then all the ones you're going to find are going to fall within that. So if you have for example, HNO3, what is the name of HNO3? What is it? Huh? It is. It's nitric acid, right? It's not hydrogen nitrate. I suppose that by normal naming, you would want to do that, but remember it's an acid, so it gets a special name. It's got an H in front. Not only is it an acid, what type of acid is it? Is it binary or is it oxyacid? It's oxyacid. Binary would only have 2 things, like HCl or HBr. This is an oxyacid. It has a polyatomic ion in its formula. So HNO3. All right, how is this going to be together? Now, these are nonmetals, so they're going to be covalently bonded together to make this acid. Okay? You'll find that the thing that makes an acid is its ability to let go of its hydrogen, to drop it off, to put it out into a solution. So somewhere along this formula, when you draw it up, there's going to be a hydrogen on the tail end somewhere, ready to fall off. And what you will find is this clue right here. The hydrogen on the outside is going to be attached to one of the oxygens. Okay? And the reason this works, by the way, is remember I said that certain things on the periodic table really like to hold on to their electrons more than others, right? So the farther you go over to the right and the farther you go up, the more they want to hang on to their electrons. Well, over there to the right and up, very close to the maximum point you can be, is going to be oxygen. Not only does oxygen really, really like to hold on to its electrons, it really, really likes to steal them from other things. It's like an electron vacuum cleaner. Okay? So what will happen is, and the reason that this can still act and form a hydrogen ion and put it into solution, even though this is not ionic, is because this oxygen right here is constantly trying to suck away the electrons that are being shared. It's not a very fair fight, is what ends up happening. So it's a balancing point where this H is just hanging on by the skin of his teeth over here. And if something else is present that could even bump this a little bit to just apply a little bit of force to this H, it'll fall off very easily, and those electrons whip back, and oxygen stole them for himself. And it leaves behind basically just a bare proton, right? One proton without an electron because it got stolen, you've got a hydrogen ion, a one positive charged hydrogen floating around now. That's why it can still be an acid. All right, so what you're going to want to generally do is put, like in this case, remember I said that nature likes to be very well distributed. It likes to be symmetrical. So if I have an HN and an O3, and I know that the H has to be on the end somewhere, somewhere, because it's going to be an acid, then that leaves me either nitrogen or oxygen having to be in the center somewhere. Since I have 3 oxygens and 1 nitrogen, basic common sense symmetry tells me to put nitrogen there and build around the oxygen around that nitrogen. Okay? So that's what I'm going to do. The first thing you do is write the skeletal structure. Okay? I think if you go back here, that's what these steps will say. It'll walk you through it. Generally, also, your halogens, like I said, and your hydrogen, halogen and hydrogen are almost always going to be, they have to be on the end somewhere, because they won't fit anywhere else, because you'll be tied up with your binding sites. You won't have any other place to put stuff if you try to stick those in the middle. Keep your symmetry. Balance things out. In oxyacids, make sure that you attach the hydrogen to the oxygen somewhere. Okay. And then keep in mind that generally your most metallic element, that's why I taught you how to find which one's more metallic on the table, because almost always your most metallic element is going to be the one that's in the center. Okay, and then everything's going to go around that. In this case, that proves true. Nitrogen is going to be a little bit more metallic than oxygen. That's why it's in the center. Okay, so what will happen here is, here's what you want to do. Once you figure out your basic structure, okay, I've got an N, 3 O's, and an H. Of these, my most metallic is N. I'm going to put it in the middle. I'm going to just draw around it. I'm going to put some O's around it. I'm going to have 3 O's. And I know that next to one of the O's, I'm going to have an H. Okay, so then I just sort of connect the dots. It doesn't have to be nice and perfect like this yet. Just sort of connect them together. Realize that, okay, I've got an N. Draw a line to an O. Draw a line to an O. Draw a line to an O. And then off that O, draw a line to an H. Okay? Now realize that everywhere you've just drawn a line represents what? Okay? 2 electrons, right? 2 electrons being shared. All right. Now, if you're going to write the rest of this structure, what remains in this structure is how the electrons are distributed, the dots around the outside. So what you're going to do then is look at the elements that you have and figure out each of them. How many valence electrons are they bringing to the table? How many are they going to bring in total? Look at hydrogen. Let's look at nitrogen first. Every nitrogen that you have is going to bring in 5 valence electrons, right? So you keep track. You're created a bank here. You're going to create a valence electron bank. Every nitrogen that you have is going to require 5 valence electrons to start with, anyways. Hydrogen that you have is bringing in 1 valence electron. Notice I only have 1 nitrogen, I only have 1 hydrogen, so I've just got 5 from this and 1 from that. Now, every oxygen that I have is going to be bringing in 6 valence electrons, right? Notice that I have 3 of them. So that means if I have 3 oxygens, I'm going to have 3 times 6 valence electrons. I'm going to end up with 18 valence electrons. So that's all that I have in this formula. So what that means is, when I'm all done, when I have figured out how to write the Lewis structure for this compound, I should have within it, I should be able to count 24 electrons. Okay? I should be able to account for 24 valence electrons that were involved in all of this bonding. So realize now you're starting with 24 electrons that you have to account for. First step now, after this, is to look at your formula and see how many you've already accounted for. How many have you already accounted for according to your lines? 8. So that's why I say used 8. I start with 24. That's how many they're all bringing to the table total. I've already, just by connecting the dots, I've used up 8. How many do I have left now? 16, right? All right, that means that what I have to now do is distribute 16 dots somewhere around this entire structure. Okay? Why do I have to do that? Because we don't create and destroy things. We have electrons that were there. They came in. I have to account for them now. And I have to look and see where they are. Okay? Where are they going to be distributed? Are they going to be anything with the nitrogen? Are they going to be all around the oxygens? How does that work? Okay, so to review, I give you a formula, HNO3. You've got to start sketching it out on paper. Draw your H, draw your N, draw 3 O's, just like you have building blocks there. Look at them and figure out a way that they can all stick together. Okay? Now, you may not be able to get it all right now, but just think about it, because what will have to happen is a couple things should play out. Number one, I have an H. This is an acid. So that means hydrogen is going to be on the end. Hydrogen will always be on the end somewhere. So that means if it's going to be on the end, it could be attached to the H, it could be attached to the N, or it could be attached to any of the O's. Well, this is an acid, and one of the clues that I give you is if you have an oxyacid, your H will be attached to one of your O's. Okay? So there you go. You can take one of your O's that you have written down, draw a line to an H. Okay? Now you have your O and your H. Now you've got your OH, you've got another O and another O. What makes sense now is keeping in mind that whatever's most metallic will probably be in the center. So you think, okay, put my nitrogen in the center. Then I'll connect that O and H that were connected. I'll connect that O, the end of the O to my nitrogen. I'll connect the other O to my nitrogen, the other O to my nitrogen. Now I've got 3 things sticking out from my nitrogen, like you see up here. Just use some common sense, and as you play with this, you'll get better at that. This is, if you understood everything just from one example, I could stop now, right? So obviously it's going to take a little bit of work. Now that you've connected these, realize that in order to connect them, what you've done is created covalent bonds to connect them. You used electron pairs to do that. All right, but you've not accounted for all the electrons that were involved in this entire process. The electrons that are involved in bonding are valence electrons. So what you've got to do is look now that you've got your skeletal structure, you've got to look at all of these and see how many each of them are bringing in terms of valence electrons. For every nitrogen that you have, you're going to have 5 valence electrons. For every hydrogen, you're going to have 1. For every oxygen, you're going to have 6. So at 5 plus 1 plus 18, I get 24 in this case. I've got 24 electrons total that have to be accounted for when my formula is complete. Okay? Excuse me. All right. Now, if I start now, I realize that I've got to count through and account for 24 of these. I look at my formula that I have connected already, and I see that I've already burned 8 of them. So that leaves me now 16 more that I have to account for. How then do I account for them? Where do I put them? That's the next step. What you will always do is try to complete octets. In other words, look at something and try to give it 8 electrons if it wants 8, right? Unless it's hydrogen, it doesn't want 8, it wants 2. So look at your octets, and what you're going to do is start from the outside and move your way in. You're going to start from the perimeter of your atom and work towards the center, okay, adding in electrons. So I'll show you what I mean. What I would do here is, imagine these dots weren't here. This is what I had on the last slide, right? I would first of all recognize and look at the fact that hydrogen is on my very outside. I might want to start there. Okay? As I look at it, I got to ask myself, hydrogen right now, where it's positioned, is it happy? Does it have the amount of electrons that it wants to have in this whole scheme? The answer is yes. It has access to 2 electrons. That's all hydrogen wants. Okay? So now I'm going to move in. My next step in is this oxygen right here. Imagine those dots were not there, and I just had line, O, line. Would that oxygen be happy? No, because without those dots, it would only have a line here and a line here. It would only have 4 total, right? 4 total electrons, 2 pairs. It's sharing these with hydrogen, it's sharing those with nitrogen, but it still has access to them. So 2, 4, no, it is not happy. So what I want to do is burn some of my electrons from my bank, put them in here, invest them into my formula here, so that I can make that oxygen happy. So how do I do that? I need to put a total of 4 more in, right? It's got access to 4. To be happy at once 8, I got to put 4 more electrons into it. So I'll put a pair up here, a pair down here. Now, I've now reduced my bank value of electrons by 4 more. See how many more I had, right? I think I had 16 to use to start with. Now I'm down to 12. I've only got 12 left to use. Well, I'm going to keep working. Okay, I've still got lots of electrons I've got to account for. I don't want to move towards the center. I want to save it for last. So now I just continue to creep around the perimeter, and then I'm eventually going to work my way in. Let's go up here to this oxygen. Notice that this oxygen only had 1 line to it. It only had 2 electrons. It needs 6 more to be happy. So I'm going to draw in 6 more electrons. Okay? Now that oxygen is happy. I'm going to move over here now. You can keep track of your electrons that you're using as you go along. I've still got some left. I'm going to move over here and look at this oxygen. Is that oxygen happy? No, it only had 1 pair, 1 bonding pair, 1 line. So I have to go in and draw 6 more electrons. Now, what I should be able to do at this point is assess my situation. Let's take a look. I need to have accounted for a total of 24 electrons. Do you have that? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've got a total of 24 electrons now. I've accounted for all valence electrons in this structure. So I'm on to something here. But I've got one problem. You notice a problem in this formula. I started outside, worked my way in. I paid attention to hydrogen. I paid attention to oxygen. Someone got neglected. What about nitrogen? Is nitrogen happy? Look at it. Nope. It's only got 6. It wants 8. What to do now? Because what I cannot do is just slap on a couple electrons and call it a day. Because we can't create electrons. We didn't have them to begin with. We've only got a certain amount that we can deal with. How does this happen? Any ideas? How can we fix this? We can't bring in anything new. We can't take anything out. But we can shift things around if we want to. Any ideas? Is there anything, let's say, that this oxygen can do? Yes, you can. Yes, you can. What I can do is take, let's say, 2 of these, for people in case I couldn't hear it. It says, can you double bond one of the oxygens? And the answer is yes. You can take 2 of these electrons right here, for example, throw them in the pool. Okay? If you throw them in the pool, realize he's not lost them. Right? He still has access to them. He would have 2, 4, there will be 2 lines here, 6, 8. That would also help nitrogen, right? So what you can do is double bond one of those oxygens. You can either do this one or you can do this one. Probably won't do this one just to balance things out because these 2 are identical. It's going to be one of these 2 that end up sharing. Okay. All right, so that's exactly right. We'll move 2 of those around. We'll get a double bond to one of those oxygens. Everything's fine. Our skeletal structure remained the same. Our total electron count is good to go. We now have a Lewis structure for this particular compound. Now, realize that it doesn't matter. It doesn't matter if I would have done the double bond here or if I would have done it there. Realize that it doesn't matter. Okay, just as long as one of them do it. We just had to pick one. So let's do this one and then take a little break after this. But I want you to write the Lewis structure for CO2. So before you cheat, before you look at it, just take a second, figure out, first of all, how these things are probably going to be oriented around each other. Okay, so don't look at the answer. Write the Lewis structure for CO2. Write your skeletal structure, what you think it's going to be, what atoms are going to be where. After you do that, what's your next step? You want to connect them together. After you've connected them together, you want to count how many electrons each of them are bringing to the table in terms of valence electrons. So create your bank. Oxygen, you got 2 oxygens. You got one carbon. How many valence electrons are they bringing in? So do that. First thing we want to do, skip all past that, is figure our skeletal structure. Hopefully you figured out that your carbon should have been in the middle. Your oxygen should have been on both ends. Right? That makes sense. Connect them together. You can see already that you've burnt four total electrons in this process, right? Just hooking them together. All right, so the next question now that we have to, or the next issue we have to deal with is how many total electrons are we dealing with? Well, if you look, carbon, you can tell by where they are in the table, or you can write their electron structure, either one. Figure out how many valence electrons they have. Carbon's going to have 4. Each oxygen's going to have 6. I've got 2 of them. So I'm going to have CO2 altogether should have a total of 16 electrons in the valence level that we have to account for. All right, now we see that we've used already 4 of them just in our skeletal structure. That leaves us now 12 electrons that have to be dealt with. All right, now remember, what I said was we start on the outside and we work our way in. So let's look at one of the oxygens on the outside. What can I do to make this oxygen happy? I can add what? I can add 6 electrons to it. So I can put 2 dots here, 2 dots here, 2 dots here. That's funny. I had my daughter. You don't care, but my daughter had a kitten a couple summers ago. She named it 2 dots because it had 2 dots on its head. 2 dots, 2 dots, 2 dots. There's 6 valence electrons here. Okay. That means I'm probably going to do the same thing over here, right? It's going to need 6 as well to make it happy. 2, 4, 6. That's it. I burn up my electrons. I don't have any more left to use because I had 12 now I could use as dots to put in. I used all 12. I can't do anything else, so I'm done with adding electrons. So what I get is this. Okay? Now, hopefully at this point, if you made it this far, you notice something was very wrong. We can't stop here. And the reason that we can't stop here is why? That's right. Carbon only has 4 electrons. We can't stop here. We've got to figure out a way to make this carbon happy, but we can't add any electrons to do it. So how can we do it? Like we did before. We can move things in and out, right? For example, I could take, well, I'll show you on the next slide. I could do that. I could move this pair into the center, and if I move that pair into the center, realize I've not lost it. It never left this. It just now became accessible to this atom, right? So if I move that in here, now I've got 2, 4, 6, 8, same as I had before. But if I didn't do this one yet, let's ignore that for a second. That would leave me now with a carbon with a single bond to that oxygen and a double bond to this oxygen. Count them up for carbon. That's still only 2, 4, 6, right? I would only have had 6 electrons. So in order to make that carbon happy, what I would not want to do, because it doesn't balance out, is bring in another pair from here and make a triple bond, right? I would have a triple bond and a single bond. That's not very even. That's not what would happen in nature to distribute things out evenly. What would happen is over here, one of the pairs would come in and do the same thing as you did on this side. So that when you do that, our oxygen still has 8. Someone knocking on my door? Oxygen still has 8. This oxygen still has 8. This carbon now has access to 2, 4, 6, 8. It's now happy. So carbon dioxide would look like this. It would have carbon in the middle, double bonded to an oxygen on both sides. So a pretty hefty bond, right? It's not a weak bond at all. And each oxygen on the outside now will actually have 4 electrons still available in its valence shell. Now realize that those electrons floating around the oxygen are not going to be very easily used to form other bonds, because what would have to happen is you would have to disrupt all this, right? If you wanted to try to share this with something else, now you've made too many electrons for oxygen, so that's not going to work. They're just going to stay the way they are. They're going to not participate in the bonding, but they're going to help achieve stability with that particular atom. All right. Easy enough? Some of you say yes. All right. Let me do this problem. I know I said we did the last problem, but this fits in with it, so we're still thinking on the same train here. I'll do this problem, and then we'll take a break, and then I'll go a little bit more. All right. Polyatomic ions, Lewis structures. everything is the same that we just did. Okay, the only difference here is when we count up the number of electrons that we need. Remember that when we have a charge, we have ions, right? So that's going to affect how many electrons we're dealing with. For every, like if we have a -1 charge, we're going to throw in an extra electron. If we have a +1 charge, we're going to use one less electron in our structure. Okay, that's it. That's the only difference. So let's take a look. Here's nitrate. This is similar to the HNO3 that we use, right? In terms of the nitrogens and oxygens, there's just no hydrogen here. If we have nitrate, how, as a group, is that organized? Where are the electrons and where are the atoms relative to one another? Well, we know that N is going to be central. It's most metallic, and there's only one of them. There's 3 oxygens, so put that in the middle. We've burned up 6 electrons already, just attaching them together. Let's look and see what all we've got. We've got 1 nitrogen that's going to have 5 valence electrons. We've got 3 oxygens. That makes for a total of 18 valence electrons. Now, why did I do this step right here? Notice that this is nitrate. This is not just NO3, charge neutral. This is NO3 with a 1 negative charge. That means at some point, if it became 1 negative, it has gained an extra electron into its configuration. So what that means is, I look at my 5 from N, I look at my 18 valence electrons from oxygen, I look, what I also have to factor in, though, is the fact that it's negatively charged. So that means I've got to throw in, for every number that I see up here, every negative, I've got to throw in another electron. So now I've got to add 1 more electron to this mix. Okay? So I'm going to have a total now of 24 electrons that have to be accounted for. You understand why I put this 1 here? Okay. All right. So the same thing applies. It's the same problem. The only difference was this step right here that wasn't there before. Okay. So we start off with 24 total. We've already used 6 in our bonding to stick them together. So that means I got 18 now that I can distribute around the outside. Starting on the outside, sorry, working my way in. So what I'm going to do then is obviously start on my oxygens and try to make them happy. Right now they all only have 2, so they're all going to need 6, as long as I have enough electrons to do so. And once I fill them all up with 6 more, I'm done. I've used all the electrons that I can use. Okay. So again, I could use 24, right? 6 of them got burnt in the sticking together process. That left me with 18 to use. And 2, 4, 6, 8, 10, 12, 14, 16, 18, I used all of them to put them around the oxygen, okay, to try to make all those oxygens happy. Okay, now, if I look at this oxygen, it has 8. That oxygen has 8. That oxygen has 8. But I got a problem. Problem is nitrogen. Nitrogen's only got 6, and I need it to have 8. So what can I do? Well, we already know the answer, right? We know how to deal with this. Notice that in this case, it's not going to matter what 2 electrons I move in. I can do it from any oxygen that's there. This is going to bring up another interesting point coming up after the break. But any of these oxygens will work, so just pick one, move it in, rewrite it as a double bond. There is your Lewis structure. Notice how similar it looks to HNO3, right, that we did. The only difference to make this nitric acid would be to take this pair, create a bond using it, and hook it to H. If that was true, then I'd have nitric acid instead of the nitrate ion. So it's a very subtle difference. There's small differences in the chemical world, but they have huge implications. All right. As I mentioned before, there are always going to be some exceptions to the octet rule. Like you've already seen, hydrogen's only going to have 2. Helium, well, it's not going to be bonding, so we don't have to worry about that. Boron, for example, will only have 6. You'll come across these. You'll recognize them, hopefully, when you see them. I'm not going to try to trip you up or anything. I just want to make sure you understand the basics here. Lithium likes to, achieve a configuration of 2 instead of 8 because it's only 1 away from helium. So when it gives it up, it falls back to 2 rather than trying to gain a bunch more and get to 8. Beryllium will actually share 2 to form 2 single bonds, and what that ends up being is 4 electrons. You don't have to memorize all of these. I'm just showing you that there are exceptions. Boron likes to form 3 bonds for a total of 6 electrons. What gets really hard to mess with, we're not going to touch it in this class, is when you get into the D block, where all the transition metals are, you can get things called expanded octets, where you can actually hold more than 8 sometimes. They can form really weird bonds. So that gets even more of a reason now why transition metals are so confusing. What ends up happening is they'll take the space. Those d orbitals are pretty big. They hold like 10. And any empty space that's in them, for example, can be used to do some other stuff with, and they sort of mess around with it. But what you'll find, too, is that Lewis theory is not perfect. There's just some things we don't understand, and this is the best that we've got to use, so this is what we use. But try as you might, you may run across, and I'll try not to intentionally ever give you this, because I'm not trying to, like, I get tricky or anything, but try as you might, there may be some things like nitrogen monoxide where you try to write a Lewis structure for it, it will never work. You will never be able to fully satisfy both of those. Oxygen has 6 valence electrons that it brings in. Nitrogen brings in 5. That's a total of 11. And when you account for 11 electrons and you make oxygen happy with 8 and try to make nitrogen happy, you're not going to be able to. It's just not going to happen. So you just do the best you can. You draw the best structure that you can and realize maybe something else will be figured out at some point. All right. Now, if you think back a second ago, we looked at a nitrate ion that was NO3, and one of the things that you had to do was bring in an electron pair from the oxygen to give it to the nitrogen to balance it all out. And I told you that it didn't matter which one of those you brought it in from. Right? It doesn't matter if it was the oxygen on top, the left, or the right. It doesn't matter. In reality, you can oftentimes draw more than one valid Lewis structure for one of these things you're doing. It doesn't, like, you could pick a different oxygen instead of the one that you picked. Any of them will work. So in real life, you have several compounds where that is true. It doesn't really matter which side you pick from. And realize what this creates is, instead of like one ever existing, what you get is a hybridization of all three sort of existing simultaneously. I know that's hard for you to imagine. I don't expect you to try to reason through it. Just accept it, I guess. That whenever you have a situation where it could be this oxygen, or this oxygen, it doesn't matter. What you end up with is instead of having one or the other, you sort of have all three at once. Okay. In other words, no one Lewis structure will adequately describe. It's hard to imagine, but you got to realize that these molecules are seeking the lowest amount of energy as possible, the most stability, and the most evenly distribution of the things that they have inside of them, these electrons and the energy. So if you have one oxygen over here that's donated that, and the other two didn't, what will actually happen is the whole molecule will respond and try to disperse that evenly all throughout. And again, it's hard for me to explain because we don't have quite the background here. But just realize that anytime you have a situation where you can draw more than one Lewis structure for something, you create what's called resonance. And resonance, like something resonates, it bounces off of something. Resonance in chemistry is the constant sort of, imagine it as constant back and forth between all of the possible Lewis structures all at once. Okay, so like imagine it like this. It's not totally accurate, but imagine for a second like that oxygen for a fraction of a second was being the one sharing. And then it stopped, and then this oxygen for a fraction of a second was being the one sharing. And then that stopped, and then now it was this oxygen. And all that happens all at the same time, and it sort of mixes all together. Instead of having just one structure, it resonates back and forth between all of the possible structures at once. That's called resonance. So in the case of like ozone, for example, you could have, this is O3, you could have a double bond between this side, you could have a double bond between that side. What you actually have is a constant resonation between those at any given point in time. We have to pick one to draw it because there's no way you can draw it in real time and have it bouncing back and forth. But there is something that you can do to indicate to me that you have a resonance structure. Draw a double-headed arrow between them, showing me that they're bouncing back and forth between these two forms. Okay? So if you have something where you can draw more than one, draw all of the possibilities, and put arrows, double-headed arrows between the possibilities so that I know that in reality it would bounce back and forth between all of these possibilities. Okay? I will show you this, though, that, like I said, in reality, you would assume, for example, that if this were true, this double bond is stronger and pulls these closer together than what that single bond does, right? So if we were measuring this and looking at it, you would think that you would see shorter here, a longer bond here. Likewise, if I was looking at this form of it, I would see a longer bond here, a shorter bond here. But what you actually see, because of resonance, when you look at this and you measure it, what you actually see is a hybrid between the two. For example, a single bond, say it's 147 picometers. Okay, really, really, really super tiny. And a double bond is 121. It's shorter, right? 121 picometers. What you would actually see in the case of this, as a result of this resonance, is an actual bond length of about 128. It's in between the two because of resonance. It's bouncing back and forth between a single and a double so fast that it actually creates a hybrid between a single and a double. So that's what we're dealing with here. All right. Because realize it's sort of like this molecule gets trapped into a vicious cycle. It is constantly trying to readjust itself so as to minimize its energy and create more stability. So as it's existing for a fraction of a second right here, it immediately sees that it can move and shift this over here because this side can become more stable if we can shift it over here. Well, as soon as it does that, then the other side realizes I can be that way too, and it shifts right back. So it's this perpetual cycle of trying to shift back and forth because it never actually gets to the point where it wants to be. It's searching for that stability, so it's constantly back and forth. It's like sort of like that shirt that says, how do you keep an idiot busy for however long, and then it says on the other side, like, see other side. Then it says on the back, how do you keep an idiot busy? See the other side. You just keep bouncing back and forth between both sides of the shirt. It's sort of the same thing here. This is acting like an idiot, and it's trying to bounce back and forth because it sees something at once on the other side, so to speak, to try to achieve that stability. So you get a constant resonation between those. Okay. All right. So if we go back to our example with the nitrate ion, right? Here's our Lewis structure. That's one of them. We could draw another one as well. What we could do then is, now remember, in terms of electron pool, whatever we put in, we got to pull out, things like that. What I mean is, like, if you're going to take this and you're going to make the double bond be over here instead of over here, I got to take this pair and put them back out as free electrons. Then I have to take these and put them in, right? So I would get something like this, and then I would show this structure, right? Then I could do the same thing for the one up here that I haven't done yet, and ultimately I would get another one down here, and I would have three, and then in between them I would draw double-headed arrows, and that shows me that there's three resonant forms of this particular compound. You will have to draw a resonance structure, at least one, on the exam, on the short answer part. So make sure you study how to do this. Now there's a lot that goes in, because I could just ask a question, for example, draw the Lewis structure for a nitrate ion including all resonance forms. There's a lot that goes into that, right? Think about it, because you'll have to know what the skeletal structure. You'll have to know how to count your valence electrons. That means you'll have to know how the periodic table works. You'll have to know how valence electrons work, how many things have what. There's a lot that goes into that one little question. It's good and bad. Bad because if you haven't been following us up until now, you are going to be lost. But good that you probably will realize you don't realize what you have learned and what you have understood to get to this point. If you actually sat down and realized all of that, you might be impressed with yourself, or disappointed, one of the two. Depends on how it works for you. Okay, so now, yes. Back on my last slide. Yep. Right. What I mean, I didn't write the arrows in right there, but what you would have is, I can't draw with this very good up here, so I'm just going to write an X. Well, I can't. This is not. Oh, here's a marker. Let's look over here. If I have whatever my structure is, I'm just going to say that X represents this guy right here. Okay. So there's my first structure. Then there's my second structure, and here's my third structure. Okay. All that you would have to do is write out all three, and then just do this. Yeah. That's all you got to do. And that shows me that those are the three resonant forms for that Lewis structure. Okay. Now, the pinnacle. We're putting it all together now. Because we haven't built up enough, we haven't accumulated enough knowledge. We've got to continually press forward, onward towards the prize of ultimate knowledge. Okay. So you're all going to take Chem 2, then you're going to take physics, right? You're going to take the calc sequence so that you understand all the math involved. There you go. No better way to spend your life. Examining all that is, questioning, asking, seeking, never settling just because someone said so. I hope you guys do that. I hope you don't just blindly trust someone just because they say something. Right? You just, not even me. Don't even trust me with all of this. Seek it out yourself. Check the data. Read all the original reports that all this stuff came out in. Or you just trust me, right? I could be making it all up. You don't care as long as that's what's on the test and you can pass the test. Oh, for crying out loud. Okay, you come up, if you want to argue every single question on the test, I say go for it. But you have to have a pretty dang good argument. You know, learn all that other stuff, bring in somewhere else. If you have alternative theories, I'm willing to listen. You better have a good case. All right. Now, see, you could get away with that because of what we learned with quantum mechanics and how it challenges reality, right? So, you know, in reality, you could say, I got an A on this exam, even in your reality if I got an F, right? So, but you have to prove it and you have to philosophically reason it to the point where you've convinced me, okay? Yeah, probably not. All right. Now that we know Lewis structure, and we've got an idea as to how things look on a sheet of paper, now we've got to make it look like it does in real life. Because if I drew you, you would be on a piece of... Well, first of all, I can't draw, so you would not want to see when I drew you. But if I drew you on a piece of paper, that is not what you look like in real life, right? Because we exist in 3 dimensions. It would look like just a picture of you on paper. Well, that's what we're doing here. Realize that when you draw this on paper, all you see is a carbon in the middle and 4 hydrogens coming off of it. But when you look at it in real life, it looks more like, you know, like a pyramid almost, as opposed to just a flat thing with a bunch of right angles on a piece of paper. So it's going to be different. What we have to do now is take our Lewis structures, understand them, and now create real situations with these molecules, what they look like in real life. Okay? Now I'm going to keep it simple. Some of these things, the more advanced chemistry you get, I know you won't think it's simple, but as the more advanced chemistry that we get, molecules, you can't name the shapes of things. They become incredibly complex and stacked on each other and really big, especially in organic chemistry and in medicine and in a lot of synthetic kind of things. But I'm going to just name some basic shapes that you can see and realize this will not characterize every possible shape that you will see with a set of atoms, but these are some very common basic ones. Okay, I'm going to go over a few of those just so we know what we're talking about. Again, everything exists in 3D, 3 dimensions. Actually, 4 after Einstein, because time would be the 4th dimension, but never mind. We are going to name these shapes according to geometric figures that we may be familiar with. Okay, what we're going to do is use this as your base reference. Okay, so look here at this particular arrangement. Use this as your reference and realize that this is sort of like a pyramid. If you could take flat like sides and stack them on here and use this as your core and like use this as your frame and stack sides on here, you would have a side here, a side here, and a side here, 3 sides, right? And a base. You would have 4 sides to this total. You would have like a pyramid type of structure. Now, in a pyramid, you have 4 corners. Okay? If this was it, you had the peak, and then at each base, you've got a corner. We're going to use these corners, these 4 corners, as our points of reference, and this is how we're going to identify these different shapes. Okay? What's happening in any of these corners? Are they all there? Are any of them missing? That kind of thing. Okay? So stay with me. What will happen as a result of this is there will be specific angles. We're going to get into what's called molecular geometry. Molecular geometry, the bond angles associated with the shape of molecules. Like this, for example. If you drew this on paper, I'll show you the difference between 3D and 2D. Do this on paper, and I had you draw carbon in the middle and 4 hydrogens. You would space them out equally from one another, and they would have all right angles between them, right? That would make sense. That's a 90-degree angle. In reality, however, what will happen is this, because you will see that the hydrogens want to move as far apart from each other as they possibly can in 3 dimensions. You end up with an angle that's greater than 90 degrees, right? See that? That's actually about 109.5 degrees. So 3 dimensions makes a huge difference. Okay, it gives these things a little bit different properties than what you would draw in 2 dimensions. So bond angles then are going to be the angles, for example, right here. Now this spring would represent obviously bonding, right? A covalent bond between carbon and hydrogen. Here's another covalent bond between carbon and hydrogen. A bond angle would be this right here, where this hydrogen seems to be located, and that one. If you drew an imaginary line, down to the carbon and across, what would that angle be right there? That's called a bond angle. Okay. All right. We've got some simple ones. We'll start with an easy one. A linear shape. Okay. If something has linear geometry, it's shaped like a line. So the angle of a line then is 180 degrees, right? Easy enough. If I have 2 atoms on opposite sides of a central atom, for example, carbon dioxide, remember you drew the Lewis structure of it. You would have carbon in the middle. You would have oxygen on both sides. That is going to be a linear geometry. The angle from what's attached to one carbon to the other hydrogen or the other oxygen that's attached, that whole angle there is going to be 180 degrees like you see up here. All right, easy enough. Now, there's something called trigonoplanar. What does that mean? First, you got to know what plane means. A plane, if you think back to geometry, is defined as everybody else says, well, forget that then. Think back to geometry. A plane is defined as 3 points in space. Here's the way you can think of it. Like a sheet of paper is a plane, right? It's like a flat slice that can be like a side of something. Okay, a piece of paper. The surface of this table could be a plane. Any sort of flat surface or whatever. So if something is a plane in terms of geometry, what you would be looking at, or molecular geometry, if it sets on a plane, is, think about this. If I had this thing sitting on a piece of paper, or if I had it sitting, if you guys can see it or not, if I had it sitting on a table, does every single atom touch the table? That means all of them are on the same plane. Okay? That's not planar, because that central atom is not touching. Okay? So if I have a planar atom, a planar geometry, it means that everything can be drawn. It's like you would draw it on a paper, like it would be flat on paper. Everything would be all in a line. Like if you picked it up and looked at it from the side, they would all be in line with each other. They would all be touching if you put it flat on a table like that. Okay? So the fact that they're all flat like this, and there's 3 things sticking out from them. Okay? Notice the shape. Looks like a triangle, right? It's not a pyramid, because a pyramid means 3 dimensions. A pyramid would mean something more like that. You're starting to get more like a pyramid when something bounces up toward the top. Here we're flat. We're just a triangle like on paper. So we call this trigonoplanar. Trigonal for the triangle, planar because they're all flat in the same line with each other. Okay? Trigonoplanar. Linear, like this, right? Trigonoplanar, like this. Now notice the bond angle for trigonoplanar. Keep in mind everything wants to spread as far apart from each other as they possibly can. So, given that all the way around is 360 degrees, if you've got 3 things that want to spread apart, what's the maximum angle that each of them can give? In other words, the 3 slices of the pie here, what are these angles going to be? It's 120, right? 120 times 3 is 360. So the bond angle there is going to be 120 degrees. Okay, easy enough. What do you mean? Right? Oh, because that line right there looks like it's coming at you? Yeah, well, yeah, ignore that. I never even thought about that, but yeah, I see. Because in actual if I want to exhibit 3 dimensions, I draw something like this. That's coming at you. Okay, well, pretend like they're not. It's flat. All right, now if I have four things, what I will have is I can have what's called, not up here, tetrahedral. Okay, tetra means four. You ever play the game Tetris? On Nintendo, every shape is made of 4 blocks. That's why it got its name. Okay, tetra means 4. Hedral is just a generic word for shape. So it's a shape with having to do with 4. In this case, 4 bonds or all 4 corners that we were talking about. Tetrahedral is like this, like the jacks or something that you would like the jacks that you would play or whatever. They have 4 atoms surrounding a central atom. Okay. Now this is in 3 dimensions. There's no way really. We don't have a name for this because it doesn't exist really. This all flat, like planar with 4 things. You'll see that will never exist. Trigonal planar can exist, and you'll see why a little bit later. But if you have 4 things stuck together, you're always going to have tetrahedral. Okay. So we've got linear. It looks like this, right? We've got trigonal planar. It looks like this to you, right? Everything's flat. And then we've got tetrahedral. So keep those shapes. Now the bond angle for a tetrahedral, 109.5. Bigger than 90 because in 3D everything wants to spread apart as far as they can from each other. So you might say then go back to trigonal planar. In 3D they could actually spread out more than that. But there's a reason that they don't. And I'll explain why. Okay. So how do you predict molecular geometry? How do you come up with what shape something's going to have? There's something called the Vesiper theory. Stands for, anybody know? Oh, how'd you figure it out? Valence shell electron pair repulsion. Okay. What that means is what I just said a second ago. They will spread out from each other as far as they can because electrons have the same charge as other electrons. We know that like charges repel each other, right? So if I have 2 things together, and if I have this molecule right here, and what I will not see is these 2 hydrogens stuck like this, all close to each other. No, it's not going to happen because they possess, these pairs right here being shared, these electrons, possess the same charge, so they're going to want to spring off from each other. They're going to want to separate out because, sort of like if you had 4 magnets, right? And you had 4 north ends of the magnet, all the same end, and you put them together, they're all instantly going to push away from each other in all directions to try to separate out from each other. That's exactly what's happening in this structure. Okay, these springs represent shared pairs, so they're not going to want to get close together. They're going to want to get as far. This one's going to get as far apart from that one as it can. Likewise, from that one and from that one, they're all going to try to spread out. And there's a point reached in space where they've reached as far as they can go to spread out from one another, and that's the angle of 109.5 in this molecule right here. Okay, that's called the Vesiper theory. The valence shell electrons, the ones that are involved in bonding here, are going to try to push each other away as far as possible. Now you will find here in a little bit that any lone pairs of electrons, like if this was not here and there was a little, like 2 extras buzzing around here that were not involved in bonding, but they were just there, they also can push things away. Okay, they can act like bonding ones and disturb the shape and push electrons away from them. Okay. So any valence shell electrons can repel each other. Okay. That's what I just said. So, all right, so each bond that you have will be an area. I'm going to talk about electron areas. Those are going to be places where they try to move away from each other. Every bond counts as an area, and every lone pair of electrons will count as an area that will try to push each other away. Okay? It doesn't matter if you have a single bond or a double bond. Like between this 2, this could be a double bond. Doesn't matter. It's still one area that's pushing away. It doesn't push more or less than the other areas. It could be a triple bond. Same thing. As long as there's some sort of bonding pair of electrons, no matter how many of them there are from here to here, that counts as one area that's pushing away from the other areas. Okay? Likewise, if there's any lone pairs of electrons just floating around, they count as an area as well. Okay? All right. What will happen, though, is molecular geometry will be slightly disturbed because if you have a lone pair, they are not tied in to this bond area right here. If this was gone and instead there was 2 electrons just buzzing around the top of this atom, they actually spread out and occupy a little bit more space than what a bond group would. Okay? They have a little more free reign. They're loose. They're free electrons, right? They kind of just spread more around this area. What happens is because they spread out a little bit more than what these guys would spread out, they actually end up exerting a little bit more of a repulsive force down. So these things get pushed down a little bit farther than they normally would get pushed down. Does that make sense? Do you see what I mean? If I had a bonding group here, this is all the farther these things would spread out from each other. But instead of a bonding group, if instead I had just like two free spinning electrons up here, what would happen is these would probably get pushed down a little bit more because these two electrons now occupy more space. They can cover more area and exert a little bit bigger force downward. So your bond angles are always going to be different, but I'm just teaching you the most common ones for reference points. Okay? Just note that they can be affected by things like that. Okay, so here's a linear shape. We've talked about that already. CO2 is an example, 180-degree bond angle. You've got two areas of electron repulsion right here, this double bond and that double bond. So it makes sense that if you have two areas like that and they want to spread as far apart as possible, they're going to go on opposite sides of each other. That's what creates this linear geometry. 180-degree bond angles. Okay, what about trigonal? When you draw a Lewis structure, for example, maybe it ends up like this. But in reality, what will happen is this guy right here, that bonding group, will probably move up here somewhere and separate out the 120-degree angles and get as far apart from each other as they possibly can. Right? So in a trigonal type of geometry, we're going to go back to our word, trigonal planar, here in a second. But we've got three areas. Tri means three. What that indicates is that I've got three areas now of electron repulsion going on. It's going to result in 120-degree bond angles. Now, here's where it gets a little bit tricky. I want you to think about this and follow me, and we'll end on this. But if I have this situation, so pay attention because it's going to get a little tricky. If I have this situation like this, and I just have, like what you see down here or whatever, an atom in the middle, three things around it, and I've got all three of these repelling each other. Okay? If all of these are bonding, in other words, like you see here, all the electrons that I'm concerned with right here are bonding electrons. They're involved with the bonding between carbon and hydrogen, for example. Then this is going to be trigonal planar. I'm going to set it down. All of them should be able to touch the table. There's 120-degree bond angles there. They all pushed apart the same amount. However, here's what's important. What if I had this arrangement, but instead of having this thing bonded to it, I had this? I'm going to leave this spring. And what this spring represents is not a bond, but two electrons that are just buzzing around the top of this atom. Okay? They're not involved with bonding, but they're there. They would be two dots on your Lewis structure right above this atom. Okay? Now, if I have this, what you've got to realize is that as I'm looking at this, imagine it's flat, okay? Because those two electrons are there, they still exert repulsive force, right? Even though they're not hooked onto a bond, they still push these guys away from each other. Now, when I look at this molecule, it doesn't look trigonal planar because in reality, you don't see this. You don't see electrons. All we see is atoms. So does that now look trigonal planar to you? No. It has a different name. It's called bent. Bent. Okay? Now realize why it's bent. It's bent because, in reality, there are electrons up here pushing down on the other two shared pairs. Right? So it's giving it a shape. It's making it... If we could see electrons instead of the atoms, if we were looking at the way the electron forces were moving, it would look trigonal planar. But in reality, we don't see those electrons. So the only thing that we actually see when we're looking are the atoms. They're bent because of this force that's being exerted up here. But right now, this is still bent. So if all the bonding, if everything's involved with bonding, we get trigonal planar, which is this. Right? However, if one of these is a lone pair, there's only two bonding, but one of those areas is actually just a pair of electrons not involved in bonding, we get bent. Okay, you see how that works? All right. Gets a little confusing. You got to be able to sort of see it in your head. So, all right. Let me end with this one. Tetrahedral is an easy one. All four are present, right? All four corners of the pyramid are present and accounted for. Okay. Take a look at this. Is the molecule I'm holding. It's the same one on the screen. It's a methane, carbon, 4 hydrogens. 4 areas of electrons around the central atom. I've got all of these occupied. When I went back to the other one I just did, notice that you can still account for, well, we can look, I'll do it, I guess, here in a little bit, but next time. I won't worry about it now. But you can account for all 4 areas. Like I was talking about 4 corners and things like that. You got to keep that sort of image in your head. When you're talking about tetrahedral, notice that all 4 of those corners that I was talking about are occupied, okay, in 3 dimensions. If they're all bonding, this is where it gets interesting. If all of these are bonding, you see all the atoms as a result, and you see what looks like tetrahedral. However, what if I had 3 bonding in 1 lone pair? So let's say I had this. Okay, now this is a little different than what I just showed you last time, okay, because I've actually got 4 things sticking out instead of 3. Right? In this case, I started with trigonoplanar as my basic shape, but this pair right here no longer is involved with bonding. It's just floating electrons, but they're still exerting a repulsive force. Okay? So what does this look like? I don't see this, is what ends up happening, but I see this. So what is this? This is not planar anymore, right? So I can't call this trigonoplanar, but I can call it trigonal. I'm going to call it trigonal because it's still shaped like a triangle, but I'm going to call it trigonal pyramidal, or trigonal pyramid, because it's more shaped like a pyramid now. It's bounced up in the air. See, it's not planar. It's not going down. Okay? How does that come about? Because I had tetrahedral as my basic shape, okay, in terms of the corners and the electrons involved. Electrons here, 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 and here. But the difference is, instead of having a group, an atom actually bonded here, I'm not going to see it. The electrons are still there, but I don't see anything because I can only see atoms. As a result, this doesn't get squashed down and make planar. As a result, that stays where it is because of these electrons out here, and everything's still trying to spread out. So that sort of like gets suspended in the middle. As a result, it's trigonal, but it's not trigonoplanar. It's trigonal pyramidal. It's in 3 dimensions now instead of just all flat. Okay. All right. Now, what if I have 2 bonding sites and 2 lone pairs? So that means I started with this as my base reference. I now have 2 bonding sites. I'm going to leave 2 hydrogens, but then I've got 2 lone pairs. I've got 2 areas now that no atoms are, but are exerting forces. I don't see them, so what does it look like? It looks bent. See that? So we have to think of things in 3 dimensions is what we have to do. Okay. Now the difference is, on Lewis structure, on this molecule, you would actually have, 4 electrons that you would have to draw in, right? Because I said that these were bonding pairs. We don't see them, but they're there. So every spring is 2 electrons, right? So there'd be 2 electrons here, 2 electrons here. So you would actually have this thing floating around, spinning through space with 2 electrons over here, 2 electrons over here, all buzzing around, floating through. Okay, pretty cool stuff. All right, stop there.